Yes. So
There is a part which is not showing, just a tiny bit.
how is it now?
Just a second. I think, you see, I can read what is below. It is known that semi-classically, and the
Oh,
line
okay.
cannot be read.
Okay. So because for me this is just full screen and
I see. So,
uh, but you see the slides shifting, right?
well, you see, I see them shifting. Right, right.
Okay.
Okay.
Okay. So, but you, for example, here you don't see the last two lines.
The last, so I don't see below. It is known that.
Uh, okay. Okay. So let me, this is the full screen mode. Let me try this one. Going out of the full screen. Uh, uh, how is it now?
Uh,
Uh,
yeah.
भाई 4 बज गया ठीक पता
No,
so
no.
maybe if I do it this way, you can
Yeah,
see the
sure.
whole
Do it
slide.
that way, we can
Okay.
see it actually. Okay.
Okay. Okay.
Okay, sure, sure,
So, okay. Now let me mute myself and
sure. So we are waiting for Behnam to introduce you,
mm,
and then we shall start. So Behnam, are you here?
hello, Shahin. Hello, Bayram. I introduced it by a slide. Uh, Shahin, you can begin. And if you, Bayram, don't have anything to say, it is a starting time. Thank you.
Is the starting time? Okay. So welcome back to the afternoon session. Let me introduce you my good friend and a very fine researcher, Professor Shahin Sheikh-Jabbari. He's going to talk about reloading black hole thermodynamics with Noether charges. Shahin, please start.
thank you. Thank you, Byram. Thank you, the organizers, for giving me the opportunity to present this recent papers that we did with the group of people that you can see here, their names. Uh, so these are very recent work, and there are many different aspects to these two papers, but here I want to stress more on what we discussed in the second paper, this one, which is basically shedding light on the question of can you hear me well? Sorry, can you hear me well or not?
Uh, Shahin, we can hear you well, but I think somebody needs to mute their actually speaker. Salih, Shule, is it Shule? Yeah, Shahin, please continue.
Whether you're hearing me well or not.
Yeah,
So,
I hear you well. I hear you well. So what happened?
uh, something happened, so let me share again. Byron, can you hear me well?
Yes, Shahin, perfect.
Sorry. So this talk will have two main results, the two main important outcomes. One is basically shedding new light on the question of charges in general relativity in general. And the second is re-derivation of Smarr relation for black holes and the first law of thermodynamics. This is basically the second part is an extension of what Iyer-Wald did about 30 years ago. Okay. So let me start by some very general statements that I'm sure you're familiar with, but just to get started. General relativity is characterized by two main features. One is equivalence principle, which is manifested in the theory through general covariance. And the second is background independence, meaning that all the geometries that provide the background for all fields, including metric itself, are out to be solutions of the same theory. So these two features are basically the very characters of general relativity. And general covariance in the field here in the general relativity appears through diffeomorphism invariance. And background independence is essentially nothing but general covariance over the solutions, space of solutions, over the field space. So this is, I think, a new way to think about background independence, and that would be a very important feature in my talk. These two features, namely general covariance on the spacetime and general covariance on the solution space, leads to one of the long-standing problems in the GR, namely defining covariant conserved charges, like mass angular momentum and so on. On the other hand, we have black holes, which are a general class of solutions to GR. And the very characteristic feature of a black hole is the existence of an event horizon, which is ideally a null surface separating spacetime into inside and outside of the black hole. Black hole, as you know, is a localized object, localized in spacetime, and carries some charges like mass, electric charge, angular momentum, and so on. It's also well known that black holes semi-classically obey laws of thermodynamics, and in particular, they have entropy. Moreover, like usual thermodynamical systems, black holes are expected to obey some relation which is mimicking the Gibbs-Duhem relation in thermodynamics, known as Smarr relation. So that's basically the derivation of the fact that, or the proof of the fact that black holes obey laws of thermodynamics has a long-standing history starting from mid-1970s. But the Iyer-Wald paper in 1994 provides a first principle derivation of the first law of thermodynamics for stationary black holes with a bifurcation killing horizon. Iyer-Wald work is very elegant and has a very good level of rigor. It connects the first law of thermodynamics to the diffeomorphism invariance of the theory, the general covariance. Basically, it proves that any generally covariant theory of, or generally invariant theory of gravity, if it has black hole solutions, that should obey first law of thermodynamics. And it builds upon the seminal work of Wald, appeared in 1993, which establishes that black hole entropy is a Noether charge for stationary black holes with a killing horizon, with a bifurcated killing horizon. However, despite very deep insights and elegance, it uses notions of charges that are not as rigorous as the whole setup used in the proof or derivation. Moreover, Smarr relation that I mentioned earlier still lacks a rigorous first principle proof. There are some papers trying to basically derive Smarr relation the same way that Iyer-Wald did for the first law, but there are many loopholes in those derivations. Okay. There are various different ways to define charges in general relativity. It has been so in the, I think, starting by Komar in late 1950s on. There have been many different ways to define charges, and each of them has its own strong and weak points. The formulation that I think is very well suited, and this would be my focus in this talk, is the covariant phase space formalism, which makes manifest diffeomorphism invariance of the theory, both on space-time and on solution space. This is why I think this is the appropriate way of studying charges, because it has the features of equivalence principle and background independence at the same time. Covariant phase space formalism is essentially a fully covariant extension of Noether's theorem for defining charges. It provides a setup to define surface charges associated with local and also global, for example, Killing symmetries, if you wish. And its development started in mid-1980s by Krenkovich and Witten, and then Lee, Wald, Iyer-Wald, Wald-Zuppus. Wald was a main figure in developing this formulation, and today still Wald is working on various extensions of formalism.
علامتش ایرادی ندارن. تنها چیزی که ایراد میگیرن که مثلا ایشون موضوعش سال 88 بوده، چرا با موسوی بوده یا با اصلاح طلبان. همینطور اندیشگی نکرده. حالا ممکنه البته
There are some very good reviews on this, but I would like to mention those which I have contributed to. In particular, we have a very good chapter in our book we wrote with Daniel Grumiller last 2 years ago. So I'll basically sketch through the formalism in a bit. So this is the outline of my talk. I'll review very briefly the basics of covariant phase space formalism, extend this to the cases where the boundaries can fluctuate. And basically, I'll try to first show that why this covariant phase space with fluctuating boundaries, this formalism, is how it sheds light on the long-standing problem of charges in GR in general, and then use this to basically improve on the derivations of Smarr relation and the first law for generic stationary black holes. And I'll argue how this derivation extends and generalizes what Iyer-Wald did or the previous attempts to derive Smarr relation. Okay, so in physics, we usually deal with a Cauchy problem, and a Cauchy problem basically tells us how the initial data defined on a Cauchy surface C is propagated in the space-time. And we know that in any mechanical system, in any theory, space of solutions actually is a phase space. It's equipped with a symplectic form, and this formulation basically tells us how to compute the symplectic form for the general class of solutions for a field theory, for any field theory. And how the symplectic form is given by an integral over a constant time slice, named the Cauchy surface. Besides having a constant time slice, a Cauchy surface, usually the problems of interest have also a boundary. By boundary, I mean a codimension 1 time-like or null surface B. And in general, the problems we are dealing with in any field theory and also in general relativity is a boundary plus initial value problem. And besides the initial data defined on a constant time slice, we need to also provide the boundary data to determine dynamics. But the point is, the interesting point is that the initial and boundary data both can be arranged through symmetries. And basically these data, initial and boundary data, furnish representations of the appropriate symmetries. On the other hand, Noether's theorem also relates symmetries to conserved charges. So basically, combining these two statements means that initial and boundary data could be represented through some charges in general. On the other hand, also, Noether's theorem, despite being very elegant, while it's covariant, it's very elegant, it's not covariant over this space-time or the field space. The reason for being not covariant on space-time is that it basically considers a specific time coordinate, for example, on t equals 0 surface, and it's basically chooses a specific time direction, so it's not covariant. And it's not covariant on the field space because it usually considers small perturbations around a given background. So it's not covariant neither on space-time nor on solution space. That's standard Noether's theorem. But this covariant phase space formalism actually helps with extending Noether's theorem to overcome these two shortcomings. Noether charges are generically given by integrals over codimension 1 constant time slices. And in theories with local symmetries like Maxwell theory or general relativity, these charges are given by not volume integrals, but integrals over codimension 2 surface integrals. Where S here, the codimension 2 surface, is the intersection of the boundary and the Cauchy surface C. So that's basically how you can imagine this. The C, the green surface, is a codimension 1 surface in the space-time M. It's a constant time slice, if you wish. The pink region is basically the part of the space-time, this MB is the part of the space-time that I'm interested in, and I would like to formulate my physics within this part. It has a time-like or null boundary given by this B, the red color. And this C and B intersect each other on a codimension 2 surface S. So basically the problem that I'm going to consider is that I want to formulate my physics over this MB. And you can imagine that all of this is basically embedded into this boundaryless hypothetical space M. And I will also be assuming that this S is compact and by definition is space-like and smooth. So all the integrals over all the integrals of total divergences over this codimension 2 surface are set to 0. Okay, that's the setup that I'm going to consider. Okay. As I mentioned, covariant phase space formalism can basically overcome the shortcomings of the Noether theorem. However, just to compare with the Noether theorem, covariant phase space formalism leads to charge variations over the solution space, unlike the Noether theorem, which leads to charges themselves, not the variations. So there comes the question of integrability of the charges over the solution space if we use covariant phase space formalism. On the other hand, like the Noether's theorem, Noether's charge, there are some freedoms, ambiguities in defining charges through covariant phase space formalism. For example, as you remember from standard textbooks, Noether's theorem, basically Noether's charges would change if you add a total derivative term to your Lagrangian. So this is, and since the theories are defined up to, or the equations of motion are classically are defined up to total derivative terms in the action, Noether's charges have some ambiguity, some freedom by the addition of a total derivative term. Covariant phase space formalism has some other similar, but conceptually similar freedoms. And one needs to deal with these freedoms and basically one should try to fix these freedoms to specify the charges. What I'm going to do here in this work, and that's basically what we did in our first paper that I just mentioned in the first slide, is that usually we basically take this C or B, or this region inside MB, basically this part, to be a fixed given surface in the space-time, for example, a constant time slice, or a constant radius in the space-time, like this B. And then compute charges. Then what basically one needs to do to overcome the issues that I mentioned, basically the general covariance, and to make the general covariance and background independence explicit, is to allow for these boundaries to fluctuate as well. So instead of considering a constant time slice, you need to allow for this so-called constant time slice to also fluctuate. And similarly for the boundary B. So that's basically the setup that I'm going to discuss. Before going into the formalism, I would like to make a comment on the boundary versus corner. Corner means codimension 2 surfaces. Boundary means codimension 1. So basically the charges that we usually compute using covariant phase space formalism are only defined by the surface integrals, integrals over codimension 2 surfaces. However, we usually build the solution space, as I tried to describe, for a given boundary. That's basically a codimension 1 surface. So while the charges are given by the integrals over corners, the solution space is usually constructed by a given boundary. Why this distinction is interesting is also one of the features that we have in the general problem of charges in general relativity. And for example, the seminal work of Brown and York, in the attempt to define charges in general relativity, has already realized that we need to define, if you want to keep covariance and, in my terminology, background independence, we need to consider quasi-local charges, meaning that they are not completely local and they are given by integrals over codimension 2 surfaces. So this is what I'm describing has a long history in general relativity. And also, it has been pointed out that this feature of these two features of general relativity, which arises as in terms of the charges as in codimension two integrals, surface integrals, has been noted that is a very salient feature of general relativity, and that's what should be kept into account when you want to even quantize relativity. For example, this paper of Jacobson has some nice idea. Okay, so let me just move to the mathematical setup. Consider a d-dimensional spacetime spanned by coordinates x mu and metric g mu nu. Let b equals 0 and c equal to 0 respectively denote the boundary B and the Cauchy surface C. And the MB that I showed in the picture that I had basically is the part of space-time specified by B positive and C positive. Okay, that's what we discussed on the figure. So let me move on. These two codimension one surfaces B and C have vectors which are normal vectors to these two surfaces respectively, but these normal vectors are not necessarily orthogonal to each other, and one may define scalar through their inner product. So if I allow for fluctuating boundary cases, there are three functions, A, B, and C, which specify the fluctuations of my boundary surfaces, the Cauchy surface, the boundary, or how the normal these two one codimension one surfaces intersect. So that's that information is in A. I can define basically induced metrics on this boundary gamma mu, or on the corner S as Q mu. And so these are just standard stuff. If I consider the codimension 2 surface S, epsilon mu nu is basically the binormal to this surface. And for the integrals, I'll be using these conventions. For integrals over codimension 1 surfaces X, which could be B or C, I use this convention. And for the integrals over codimension 2 surface S, I use this convention. So this is basically accounting for the measure here and there. Okay. So far was about the geometric quantities, which are relevant to make manifest the general covariance. But we also have the solution space, the field space. I generically denote the fields by phi and their variations by delta phi. So this delta phi are to be viewed as one forms over the solution space, over the field space. I'll use the convention PQ form to denote a P form over the spacetime and a Q form over the field space. With this terminology, epsilon mu that I introduced in the previous slide is a 2, 0 form, and delta 8, delta B, delta C are 0, 1 forms. In our formalism, there is a 1, 1 form chi defined in this way, which is a key object in our analysis. And there is an associated vector chi with upper index. Okay. Now let me go to the physical setup. I have an action defined over this MB described by this Lagrangian L of phi. And formally, as a mathematical trait, I can use the Heaviside function h of b to basically replace the MB with the boundary less manifold M. So h of b, the role of h of b is basically to restrict this integral to MB. That's basically how I get rid of the boundary information in the range of the integral for the action. And basically, this is appropriate if I want to allow for the boundary to also fluctuate freely. That's the mathematical trick which lets us do this, consider these fluctuations conveniently. Usually given an action, we basically consider the variation of the action, which leads the equations of motion here in E of phi, and boundary term. And here the boundary term theta mu is the standard Iyer-Wald part plus something proportional to the Lagrangian and the same vector chi that I introduced earlier. So this is just straightforward computation. I'll not go through the explicit derivation. So the variation of the action yields equations of motion and a boundary term, theta. One can basically start with this theta mu and find its field variations, delta theta, and define a two-form over the space-time, over the solution space, omega mu. So this is a two-form over the solution space. But by definition, this omega mu has a zero variation because delta squared is zero. One can also observe that the divergence of this omega mu is zero because the second variation of the action is also zero, delta squared. Where here in this equation, I've assumed these equations are written on shell. And importantly, I've assumed that delta phi satisfies linearized equations of motion. So omega mu is closed and divergence free, closed over the solution space and divergence free. And one can use this to define symplectic form omega as defined here. This symplectic form is given by an integral over the Cauchy surface. So that's how we define symplectic forms for field theories. And the fact that omega is divergence free, it tells us that this symplectic form capital omega does not depend on which Cauchy surface we integrate over. And this is basically what we need to have a well-defined symplectic form. And by definition, it's also closed over the solution space. So these are the two features that we would like a symplectic form to have. When we consider the case with fluctuating boundaries, if I just plug what I showed earlier, the symplectic form will have two parts. One is the Iyer-Wald part, and the other one which is coming from the boundary term in the variation of the action. And so this is omega c is, as the notation indicates, is a corner term. So it's an integral over S, the codimension 2 surface, and it involves this chi vector that I introduced. And the Iyer-Wald part is basically a boundary integral. It's a codimension 1 integral, whereas the corner one is a codimension 2 integral. And here the wedge is the wedge product over the field space among the forms in the field space. Okay, so this was a general formulation how one can define symplectic form for a given Lagrangian. As I mentioned earlier, there are two freedoms in defining the theta mu and the associated freedom which is induced over the symplectic form. One of them is the W freedom, which is basically one can define the Lagrangian classically up to total derivatives. There is also a Y freedom, recalling that divergence of theta mu is variation of Lagrangian on shell. So theta is defined up to a total divergence term. Okay. So this is an independent freedom. So there are two freedoms in defining theta mu. So this is basically how it works. you can replace theta with this theta tilde, and these two freedoms change theta in this way, as you can see here. And this W and the Y are not specified by the classical Lagrangian that I mentioned earlier, discussed earlier. Okay. And the same way, symplectic form is also has some freedom in it. But interestingly, after long algebra, one can see that when we allow for the fluctuating boundaries, only a certain combination of these W and Y, shown in Y bar, in this combination, appears in the modification of the symplectic form. Okay. So not W or Y independently, but this certain combination appears in the transformation or the freedom of the symplectic form. Okay, so far so good. How do we compute charges within this formalism? Given this omega, the symplectic form, and a symmetry generator like in a diffeomorphism C, one can define the charge variation in this way. Basically, you replace one of the field variations with this delta C of phi, how the generic fields phi transform under diffeomorphism Xi. This object is now a one form over the solution space, and by definition, this is the charge variation. One can show that this is conserved, this object, because of the properties of the omega. Namely, since this little omega, the symplectic potential, or symplectic density omega mu, is divergence free. Locally, using Poincare lemma on shell, one can write it as the divergence of a two form, K mu nu. It's an antisymmetric bivector and a two form over the field space. And this delta slash psi is given by integral over the surface, the codimension 2 integral, where I use the divergence theorem to basically transform the codimension 1 integrals over to a codimension 2 integral. So by definition, this charge variation delta slash Q is a 0-1 form over the solution space and space-time. But this one form need not be an exact one form, meaning that this delta slash of Q need not be delta of some Q. If this happens, the charge is integrable, but there is no guarantee that this happens in general. So in this formalism, unlike the Noether theorem, we need to deal with the question of integrability of the charge as well. One can also define the charge algebra. Once you have the charge variation, you can basically compute this combination. And if the charges are integrable, this is basically the Poisson bracket of two charges over the field space. And one can show that this is always the charge associated with the Lie bracket of two diffeomorphisms up to a central term. So there's a standard theorem which states this for the integrable charges. Now, if we allow for the boundary fluctuations, what we get is basically the charges have two parts, a contribution from standard contribution, the Iyer-Wald contribution, and a part which is receiving contributions from the fluctuating boundaries. Now, what I would like to show in the next slide is that if we consider the fluctuations of the boundary, the charges would always be integrable, and the integrable charge is nothing but the Noether charge. Okay, so I'll cut the details of the computations and show you the main results. So going through the elaborate computations, one arrives at this expression. For the Iyer-Wald contribution, what one gets is the Noether charge variation of the Noether charge plus this combination, where the Noether charge is defined in terms of the Noether current, as you can see here. in terms of this J. J is basically divergence of the Noether charge density, and the J itself is computed in this way. This is standard Noether's theorem, but written in a formal way. So that's how we compute the Noether charge, and this part is an extra piece. And as you can see, in the standard formalism, this is the part which is not necessarily integrable. The first term is integrable. But now we also have a corner part, which the explicit expression is written here. And one can go through detailed and lengthy computations. I have written the outcome here, and that's the corner part contribution. When you add this corner part to the part that we had, the leveled part, you get the total charge, which is basically of this form. But now the point is, since we are allowing for this, the boundary of the integral, the range of the integral to also fluctuate, this is indeed a total variation. To see this, basically, you can try to push this delta to behind the integral, but this delta would then also act on this S, and one can show that's basically what we have shown in our paper, in our recent paper, that when this delta acts on this S, it exactly produces this contribution. So at the end of the day, when you try to push this delta behind the integral, the charge becomes integrable. And so these are the details of the computations, but you can see more details in the paper, of course. That's what we remain with at the end of the day. This means that the charges, when you consider fluctuating boundaries, the charges become integrable, and the integrable charge is nothing but the Noether charge. Okay, but the point is here, this equation must be viewed as a first-order differential equation over the solution space. Delta of something is equal to delta of something which is known. You can try to integrate this expression over the field space, but then you need to introduce a constant of integration, as you can see here. This QR is the constant of integration. And by definition, delta of this QR over the field space must be zero because it's a constant of integration. From the more physical viewpoint, this QR is actually the charge of a reference point, reference configuration. So this is basically the expression that one can find for QR. If we assume that we have a reference configuration, that the charge vanishes for that, it basically fixes this QR, the reference charge, in terms of the Noether charge associated with that reference frame. For example, we of any field configuration, then basically this expression is not covariant. This QR is not covariant, and the reason is very simple, actually. By covariant, we always mean something like this equation. Any quantity X is covariant if its variation along some diffeomorphism eta satisfies this equation. This is what we mean by covariance. But Qn is by definition covariant. You can just go through the definitions that we have for Qn. However, this QR is not covariant, and one can see it, it follows from this expression that we have for QR. Okay. So from delta QR equal to 0, which was the definition of QR, we learned that delta eta of QR is 0. From the covariance of the Noether charge and this definition, we learned that this combination is equal to something which isn't written here. This is just straightforward algebra. And this combination is not necessarily zero. Had this QR been covariant, the left-hand side must have been vanishing, but it doesn't. So this basically very clearly states where the problem in the definition of covariant charges in general relativity basically is rooted. The charge expression that we have is the Noether part plus a constant piece, some reference point, and the reference point is not covariant. This is what you can see explicitly. Okay. So to me, this basically very clearly addresses or clarifies the problem of the charge in general relativity. And of course, it remains to study ramifications of this, which is a separate issue. And there are many different ways to basically study its consequences. Let me skip through this and go to the main part that I wanted to emphasize. But just to summarize so far, the covariant phase space formalism with fluctuating boundaries allows us to disentangle two notions, covariance over the space-time and covariance over the field space or background independence. And these two respectively are related to the charge conservation, which is related to the space-time covariance, and charge integrability, which is related to the field space covariance. And I basically also mentioned where the non-covariance of the charge in this setup arises from. Okay, now I would like to apply this general formalism to the question of black holes. So the setup that I'm going to consider is something similar to what we had, but now I add two two surfaces, S1 and S2. And now I restrict myself to, instead of Xi, which was a general diffeomorphism, to killing vectors to exact symmetries like zeta. By killing symmetries, I mean delta zeta is equal to 0. If we have other gauge symmetries like Maxwell theory and so on in the game, this instead of being 0 is 0 up to some possibly internal gauge transformations. And what I'm going to do is basically to review, revise, extend, generalize Iyer-Wald analysis to this case, which allows for the fluctuation of the boundary. And I'm going to consider the cases where the zeta is also field dependent. I allow for the field dependence. This is for the first time that I know in the literature that this general field dependence is allowed for these killing symmetries, killing vectors. Okay. Of course, there have been many examples, in particular in the papers that we wrote in this since 10 years ago or so. So these are some relevant papers which allows for field dependence for the killing vectors or the parametric dependence on the killing vectors. So that's basically how I extend the Iyer-Wald and also emphasize and argue, I think for the first time in the literature, that how these derivations are independent of both W and Y freedoms that I discussed earlier. So this is the setup that I'm going to consider. So I've here focused on the basically suppress the codimension 2 part, the S part. So the S1 and S2 are two codimension surfaces, generic ones. And basically this is the B and C plane. This is a two-dimensional part. This S1 and S2 are quite generic. They could be space-like, null, or time-like separated. And this chi1, 2 is the some generic codimension 1 surface which connects these two. So this is the setup that I'm going to consider and rewrite the equations that I had for these cases. As I emphasized, this S1 and S2 could be time-like, null, or space-like separated. So I'm going to present to you 4 propositions which would yield general Smarr relation, generalized first law, and establishes the freedom independence of these two Smarr and first law. So the first proposition or theorem is that for any Killing vector zeta, which satisfies this relation, the difference between the Noether charges defined over S2 and S1 is always given by this expression. And this is the basis for deriving the Smarr relation. Of course, for the Smarr relation, this S1 and S2 are taken to be space-like separated. Okay. For example, S1 and S2 could be two constant radius surfaces at a given time slice. Okay. The proposition 2, which yields generalized first law, is based on a 0-1 form K, defined in this way. And one can prove that for any S1 and S2, we have this relation that this K does not depend on the choice of S in particular. If I choose S1 and S2 to be two arbitrary codimension two surfaces, but space-like separated, this equation 4 yields the first law. Okay. The third and fourth propositions are about the W and Y independence of the Smarr relation, equation 2, this one, and this relation, this K. This equation 4 is independent of Y and W. The details of the proofs could be found in this paper. Okay, so I skip through the proofs. You can see the proofs there. Okay. Now this is just with all this machinery in hand, this is just a simple exercise to rewrite the equations that I had, in particular equation 2 and 4, for the specific cases of black holes. For example, consider a black hole, stationary axisymmetric black hole with a bifurcating Killing horizon H, generated by zeta H, the Killing vector, which is a linear combination of stationarity and axisymmetric Killing vectors. These are just the usual definitions. And rewrite the equation that I had for two S's. I take one of them to be the bifurcation surface, SB, and the other one to be the I naught at infinity. So my general equation now takes this form. And one can basically try to compute the left-hand side and right-hand side of the previous equation. The left-hand side, by definition, is the Wald's entropy or variation of the Wald's entropy. And the right-hand side could also be computed. But what I want to emphasize here is that in the standard Iyer-Wald derivation, basically they took this T of H and omega of H to have 0 variations, and basically they pushed these coefficients out of the variations. But that's not actually the most general case. Here, I've tried to show that we keep these variations of TH and omega H, and they basically at the end of the day cancel out. If we kept everything, including allowing for the boundaries to also fluctuate, these fluctuations, these variations would drop out, and we get the usual first law as we expected. So in view of time, I'll just spare you with the details. You can see it in the details of the derivation is very close to what we have for in the Iyer-Wald. but you can see our paper for more details. So this was for the first law. For the Smarr relation, I just repeat the same game. I had this equation for the Smarr relation. Now rewrite it for zeta equals zeta h, and S1 to be the bifurcation surface and S2 to be I naught. And we get this relation. Unlike the first law, this relation kept some traces, explicit traces of what the theory is. So it's not that universal. And of course, we know that Smarr relation is not as universal as the first law. So this is very manifest here. And then basically one can work out the both sides of this equation explicitly. That's what we get. That's the general first law. Remember that I didn't specify the theory. I just assumed that I have a black hole with a bifurcating horizon. So depending on the theory, the form of the Smarr relation would be different, but the first law would be the same. And also remember that in the Smarr relation, what appears is the Noether mass, and what appears in the first law is sort of something which we usually call ADM mass. We had a precise definition of what precise, I mean covariant definition of what the ADM mass is. It's an sort of rigorously defined ADM mass. Okay. So maybe I need to wrap up. In our paper here, we have given several examples of this for different black holes of different theories. Theories in any dimension, you can have Lovelock or other gravity theories, and these are very general relations. You can see the examples there. Okay, so let me wrap up. I reviewed for you the formalism that we just developed in our recent papers, the covariant phases with formalism with fluctuating boundaries. And basically, this sheds light on the long-standing problem of charges and general relativity. And it yields basically integrable charges, which is the Noether charge for any covariant diffeomorphism invariant theory. This formalism actually allows us to disentangle two notions which are usually very interconnected, namely integrability of the charge, which is something defined over the solution space, and conservation, which is basically defined over the field space-time. The cases with fixed boundaries, these two are basically very much interconnected, and they could not be disentangled. But when we allow for the boundaries to fluctuate, these two become two independent notions. And actually the same thing happen, the same boundary fluctuating cases allows us to disentangle background independence and general covariance at the level of the charges. And this was the key to basically address this problem of, or clarify the problem of charges in general relativity. Okay, as I mentioned, non-covariance of the charge in general relativity comes from an integration constant over the field space. If you compute the charges and you have a central charge, the same central charge, for example, if you remember Brown-Henou analysis, the same central charge appears from the same reference point charge that I mentioned. And these central charges are basically manifestations of the non-covariance of the charges. Use this formulation to rederive some generalized first law and generalized Smarr relation, and for generic black holes, which are free of Y and W ambiguities. In particular, the extensions that we did includes field dependence, parametric dependence in zeta. One can show that this K, the 0-1 form that was the basic object in the definition in my first law, is unique if I assume linearity in zeta and invariance over W and Y choices. It's interesting to extend what I learned from my generalized first law and Smarr relations for the cases where S1 and S2 are null or time-like separated. The same formalism will hopefully allow for us to address problems regarding dynamical black holes and information problem. And I hope to report to you on these very interesting features in the next meeting. Thank you very much for your attention.
Shahin, thank you very much for the very nice presentation. And now we can take some questions. Please go ahead. Well, before maybe anybody asks, I can ask two questions, Shahin, if you want. The first one is, so what is the typical motivation in the gravity theory to consider fluctuating boundaries?
Okay. So that's let me answer this question in a slightly different way, which is related to the last comment that I made about dynamical black holes. So usually if you have a black hole and you have a horizon, take a null surface, when we have, for example, matter accreting into the black hole, or we have Hawking radiation things pouring out, basically we need to consider this null surface to allow for this null surface to fluctuate. So to formulate realistic cases, actually we need to allow for this null surface to have arbitrary fluctuations to allow for the flux of things going in or coming out. In particular, to add, this is my understanding of the information problem, that to address the information problem, not only the horizon, but also the bifurcation surface itself, the intersection of the past and future horizons, should be allowed to fluctuate. Otherwise, we'll never be able to address the information problem. The reason is sort of simple. If you are an observer sitting outside and you pour in things in the black hole, you can change the horizon, but you cannot change the bifurcation surface. If you are residing in the white hole part, you can also change the past horizon, but not the bifurcation surface. Whereas when you consider the processes like evaporation of a black hole, eventually you lose the black hole totally. There is no bifurcation surface. So you need to allow for the bifurcation surface to also have fluctuations, to have dynamics. And that's very non-trivial. So this is why these cases with fluctuating boundaries are the essential formalism that one needs to address the problems regarding any dynamical black hole, and in particular information problem.
Okay. Thank you. Any other question? Yeah, there is a question by Ida. Ida, please go ahead. You need to unmute.
Hello. Thank you for the very informative talk. So I just wanted to make sure that does this reasoning about conserved charges solve the problem with defining the proper definition of angular momentum in asymptotically flat spacetimes, for instance?
Okay. Now, please let me know if I understood the problem correctly. Let me go back to this equation where I showed where the covariance of the charge actually breaks down. Here, as you can see, the left-hand side, if it were 0, it meant that the QR is covariant. But you can write it in terms of the Noether charge computed for the reference point, and it is not covariant. But let's explore what is the right-hand side of this equation. It's variation of the Noether charge with respect to fields computed at the reference point, but it's multiplied by delta 8 or lead derivative of the reference point with respect to 8. So basically, this part is usually what we call the soft charges. for example, phi r, let's suppose that phi r is the flat space. As we usually consider the flat space is basically the reference point. This delta eta of phi r is non-zero. We know that, for example, this leads to BMS charges. Okay. What this means is that actually the non-covariance of the charges, the QR, in the reference charge, is proportional to the BMS charges, the soft charges of the same configuration. Okay. So this is what people have observed in many different examples, but it has never been as clean as what I'm showing you in this equation. So basically, this tells us that the angular momentum could be defined up to these soft charges. And there is no unique way to disentangle these soft charges from the angular momentum or the mass. But this is a very feature of the problem. It's not an issue. It's the feature.
I see. Yes. Thank you.
Sure.
Shahin, in the chat, Izzet has a question. Could you read it, or if you want me to, I can read it for you.
If you can read it, it would be.
Okay, so
would you read it, please?
Yeah, sure. Izzet is thanking for your seminar and asking about the physical interpretation of the reference point of charges.
Okay. As I said, this is a problem that needs to be explored. I just mentioned some facts about this, some comments, but if you are familiar with the sort of literature of defining charges in general relativity, this was a known problem.
Please, someone, yeah.
Okay. So, and basically, Wald and Zupas in 1999 tried to sort of address this problem in the most covariant way that they could. But if you want, the basic problem was noted there in Wald-Zupas paper. But they tried to give some physical arguments rather than mathematically rigorous analysis to fix this reference dependence.
Okay.
But for just the, I think you may look at the Wald-Zupas paper first and then go through the analysis that I just mentioned here. But that's a good question to be explored in more detail.
Right. One last question. If the charge is not integrable, still generate a symmetry of the theory?
Okay. So what I try to prove here is that if you allow for the boundaries to fluctuate, the charges are always integrable.
Okay. Nice.
That was so this statement was sort of made in these two papers by Luca Ciambelli and Rob Lee and one other guy and Laurent Friedel. But their formulation was not as clean as what I mentioned here, but the statement was also made there. So if you allow, not this statement, the statement that the charges could always be made integrable. What our addition is that the charges, if you allow for boundaries to fluctuate, and we explicitly show how this appears in the analysis, the fluctuation of the boundary is basically making the charges integrable. If you wish, I can show this equation. This equation basically, if you want to push this delta behind the integral and at the same time allow for the S to fluctuate, the contribution that comes from variation of S is exactly equal to this one with an opposite sign.
Nice, nice. Okay,
so if you allow for the fluctuating boundaries, the charges are always integrable.
Okay, great. So thank you very much, Shahin, again for this very nice talk. And if there are no more questions,